Okay, so are we ready to start? Thank you. So hello everyone, my name is Robert and this is my friend Luka. We are both from Croteam and we are here today to discuss how and why we built our custom terrain engine from the ground up for our latest game, Series M for Planet Badass. Okay, so before we get to the how, let's talk about the why. What were our motivations? So Series Sam always had, as a franchise, the same motto, bigger is better. So that means in level design, our designers always preferred to use huge open spaces instead of invisible walls or barriers to limit player movement. But in our previous games, those huge levels usually meant about 5 kilometers. But in real life, on a clear day, you can have a vista that spans up to 50 or even 100 kilometers. So this is one goal that we wanted to achieve, those realistic vistas. But at the same time, we wanted to preserve high precision detail, and that means having textures up to 1 millimeter detail. So basically what I'm talking about here is a photorealistic look. We use a technique called photogrammetry to scan models to get their realistic meshes and textures, and we did this for almost all of our environment assets. This is important because this allows us to contrast our crazy alien enemy designs that really pop out in this realistic environment. There's another problem that I would like to discuss. We like to call it the Deceptive Scale. So these are two actual photographs of two places in real life. The thing is, this photo on the right shows a very tall mountain, which is very far away from the viewer. The photo on the left shows a rather not so tall hill, which is fairly close to the viewer. But the thing is, both of these relatively look the same. Why is that? Well, because of perspective projection, of course. But the thing is, having those realistic scales is a hard problem. And most game developers, when they really try to show something like this photo on the right, they actually do something similar to the photo on the left, where they use fake scales. And they try to obscure that by using additional cheats like faked atmospheric effects and stuff like that, to make it appear like it's a very tall mountain, which is very far away. But we set out to actually solve the problem of having real life scales, and we'll tell you how we managed to do that.
So before we move on, we'll have some in-game footage here on the next slide, and we'd like to disclaim a few things. So the game is still very much in development, so the following footage will contain a lot of placeholders, a lot of possible, bugs. And the fly mode you'll see in this footage isn't available in regular gameplay, so the player won't be able to see the things we'll be seeing here. So to restate our goals in numbers, we wanted to create huge terrains, so over 100 by 100 kilometers in size, but we wanted to preserve as much detail as possible. So by using photoscan geometry for textures, etc., we were able to achieve 1 millimeter per pixel details on such a large scale terrain. As you can see in the picture on the right, we managed to preserve the detail of the small stones under the player with such high precision. The resolution of the geometry itself is, as you can see here, 1.5 centimeters in size, so that's quite high precision.
But how much data is it actually? So if you try to model everything by hand, well, let's break it down. So we have a terrain which is more than 100 kilometers per dimension. So with resolution of 64 vertices per meter, that turns out to be about 64 billion vertices. So that would be about 100 terabytes of data for elevation alone. So obviously that's a no-go. We needed a different approach. So we thought about procedural generation, like we could just generate everything on the fly. So obviously that would solve the problem of storage, but first of all, it would be slow. And second problem, it would look artificial because it's really hard to achieve completely natural and realistic looking environments if you generate everything from scratch. So our approach is a hybrid solution. Well, basically there are two main components here. Let's call them model and view. So the view is pretty self-explanatory. It's a component that renders our model. So let's look at the model itself. So we start with the pre-made data that we import into the editor. So this is really like a seed. And we allow our content creators to edit this data to add extra detail in areas of interest. But to get really fine details at really high resolutions, we use procedural generation.
So for the first step, the pre-made data, we want to have a basis in the real world for some of our environments, like on the images on the right. So we imported some data for elevation, vegetation density, and the base color to follow the theme of the real world place we're modeling here. The resolution of the imported data is 32 samples per kilometer, so the total cost, the total memory consumption of it is only 3 4K textures that gives us 144 megabytes in size, so that's not that big for the basis of the terrain. And on top of that, to add some handmade data, we allow our artists to configure to paint additional data in places of interest. As you can see on the image on the right, the extra coloring on this visualization is the extra edited data around certain side missions or the main storyline. The entire terrain, all terrain data structures are based on quadtrees. So this is basically one of the quadtrees for edited data, let's say edited elevation. And we can also paint the vegetation density, which we'll explain later, and additional data that allows us to achieve better detail.
Okay, so let's talk about procedural generation now. So there are two main areas here. That's elevation and materials, and a special mention of something called horizontal displacement. Now, let's go through each of these individually now. So elevation. Once we import our data, or even let the artists edit it a bit, it's still not in high enough resolution to use it directly. So the obvious solution is we have to interpolate it. The simplest way to do it is a cubic spline, which works well enough. And as you can see here, it produces these nice looking smooth hills. But it's not terribly realistic. So what we need is noise, and we use fractal noise. So why is it called that way? Because we add a layer of coarse grained noise onto our interpolated data. And then we add another layer of finer detailed noise. And we accumulate that and add a third layer, which adds even finer noise. So as you can see, we can keep doing this however many times we need to, and we can use this to achieve any zoom level we want. And that's the very definition of fractals. So there are several rules about how we go about applying this noise. For example, we noticed that mountains are generally more jagged the higher up you go, so we apply more noise on higher elevations. There's another concept called the angle of repose. So this refers to the steepness of a slope. Now this is something based in physics, where if you have a heap of material, you cannot make it too steep because the forces of friction will not be enough to hold that heap in place. In fact, the material will slip and it'll form a natural maximum angle of its own slope, which is called the angle of repose. So in other words, what this means is if you have some materials for soft ground, like soil, and another material for jagged rock, well, if the steepness of a slope of a hill is too high, you have to replace the soft soil material with a hard jagged rock. In terms of elevation, this means we need to add more noise if the steepness is too high. But it's also important later on when we choose the actual materials. So another really cool thing we can do is all of the stuff I just talked about is done in the vertex shader. But a vertex shader does not need to simply adjust the elevation of a vertex. It can also displace it in the horizontal plane. And if you do that, well, it's simply called horizontal displacement. But as you can see, the effect is quite striking. And you can see it better in these images here that show with and without horizontal displacement. It's a very powerful impact. And it's fairly a straightforward technique. And it's actually not that new. In fact, to my knowledge, it was first mentioned in Altera block almost 10 years ago.
After implementing the elevation and horizontal displacement generation, we ran into a problem. So our artists wanted to place some models, let's say walls or other buildings, next to the terrain, but then the terrain started to protrude through the walls, as you can see on the left images here. So no matter how high the precision we allowed for editing the elevation, it didn't work, it never worked. So our solution was quite simple in the end. We let them define vertical lines to cut the terrain and then align the adjacent vertices of the terrain. And then you get this nice cut, like in the images on the right, where the terrain simply doesn't exist anymore. So you can line any model right next to it, and there's no weird visual issues. Another thing to mention before we move on to materials, the elevation we explained so far was generated on a vertex resolution because that's all we need to displace the terrain. But we actually generated on a higher precision, up to per pixel resolution, in order to generate further terrain features like materials. As you can see on this picture here, the generation on the higher resolution allows us to generate the materials on this little hillside, which allows for much more variation in the materials. So moving on to the materials, the first part is what are our materials built of? So of course we have the base textures, albedo, normal, gloss, pretty self-explanatory. We also have a height map, also scanned by photogrammetry. So as you can see on the image on the right, we combine the height with the elevation we generate procedurally to get this fine detail to shape the cobblestones, the stone tiles in the floor, and all other fine details. And additionally, we'll explain this a bit later, we have a special grass or flowers mask that allows us to define per material which grass types or flower types, etc., can spawn on that material. We'll come back to this later. And as we said before, each texture covers a 4 by 4 meters space. So another thing related to material textures, considering that our textures are 1 millimeter per pixel, after you reach a certain distance from the player, you start to lose detail. So we had to add an additional set of textures for each material called mid-textures or mid-range textures. So after a certain distance, we just replenish the resolution, the level of detail, by just swapping in the second set of textures. But even those textures lose detail after a certain distance, so we have another set, a global set of textures that replaces every material texture on the terrain. Let's say you can relate it to like a satellite image or something like that. So moving on, how do we actually distribute these materials in the terrain? How do we decide where to place which material?
Yeah, so that's a good question, and we actually have several rules which define this. So the first set of rules is based on elevation. So what this really means is that we can create groups of materials which are defined for a specific range of elevation. So in this diagram here, we can see, for example, we can define a group which is at the sea level. It has some kind of a sandy material. Going up from there, we have grasslands. And then higher up, we have grass and ground. Even further up, we have bare rocks. And finally, we have snow-covered mountain peaks. But as you can see here, there are no sharp cuts between any two regions. The way this works is that we apply something akin to a pearly noise texture to our material map, and the result is a gradual transition between two material regions. The code for this is actually fairly straightforward. It's done in the pixel shader, and you can see here in this snippet. So another set of rules is it helps us define how we distribute materials within one region. So one group usually has 2 or up to 8 materials. And there are 2 main parameters that we use to pick materials. So that's slope and vegetation density. I already talked about slope. Here it's important to take account of that angle of repose and match it to what was used for elevation, so that we can match the texture of rock to a jagged part of a hill, and the texture of ground to the softer part. So the other thing is vegetation density, which allows us to define various regions. For example, if the density is low, then we have a dry, arid area. In the mid-range of vegetation density, we have grasslands. And then if the vegetation density is high, we have forested regions. But again, the logic for all of this is fairly straightforward. All we do is evaluate our noise function, multiply it with evaluated ramp functions for slope and vegetation density. We multiply all that together, and that's the probability of picking any single material. And then the material with the highest chance wins.
So moving on, how to achieve nice transitions between materials after we know how to choose which material to place in which pixel. So the naive approach would be just to not do anything special, so you'd get this weird blocky transition. We don't want that, obviously. The second approach is something we've used in our previous games. Other developers also use it. It's just blending between materials that are adjacent. So we get this weird combination of, let's say, stone tiles on the floor and grass that's completely unnatural. You have grass, have stone. Our approach, one of our approaches that already works good enough, is the noisy choose. So for each pixel, we combine the noise with the material parameters we have to pick which material is placed in that pixel, and then you get this nice transition, as in these images, where each pixel is only defined by one material, so you don't have any weird blurriness. This is the first idea we use. The second idea we use for some materials that have low frequency features, like the stone tiles we keep coming back to, is the height-based noise transition. So as you can see on this image here, this process allows us to preserve the shape of the stones in the transition between the grass and the stones. The stones slowly shrink as they go into the grass, but the shape is preserved, and the grass slowly seeps into the crevices between the stones. The process is fairly simple. We just combine the noise with the height of the materials. And this is a comparison. On the left side, we have just the noisy choose process. So this looks fairly natural. I could sell this as a photograph. So unless you look very closely, you don't see any issues with this. And on the right side, this is an in-game screenshot. You see the height-based noise picking. I think it looks nice.
I think so too.
Thanks.
Okay, so that basically covers all of our model, or all of our data. So let's talk about how we actually render all that data. So the basic component is a Quadtree Renderer. The basic unit is a tile. Now, the important thing is that a tile is a fixed size in terms of it always has 33 vertices per dimension. And it always uses the same texture size, which is 512 pixels per dimension. Now what changes is that those tiles which are closer to the viewer cover a smaller area, and further away tiles cover more and more area. So the smallest tile is half a meter size per dimension. The layer after would be 1 meter, then 2 meters, 4 meters, 8 meters, and so on. What this turns out to be is that if you want to have twice as large a terrain or twice as far a view distance, you only need to add 9 new tiles. So in other words, with 18 levels, which turns out to be about 160 tiles, you get a terrain size of 128 kilometers. Or in other words, we only need about 350,000 triangles to render a typical scene, which is great because by today's standards, this is really not that much.
So all this combined, the renderer with the procedurally generated data and the imported data and the edited data, we get this. Is the bare terrain, doesn't look very interesting, but it's nice for a base. Moving on, we have additional rendering subsystems incorporated into our engine. So the first one is forest imposters. Further away from the player, we just can't render entire models. It would be way too expensive. So we render forest imposters based on some parameters the artist set. And close to the player, we render, of course, actual tree instances. The actual parameters for placing these, the rules for spawning these are quite complicated, but yeah, there's a lot of them. Additionally, we have a similar system for plants and crops and other models we may like to spawn procedurally on the terrain. So yeah, the artists can configure those as well. And moving on to finer detail, we have grass, as we mentioned before. We'll come back to grass later. And we have flowers for even more detail.
Okay, so let's first talk about forest imposters. So first off, we really wanted to have our forests visible up to very far away draw distance. So we opted for an entirely GPU-based approach, and this allowed us to achieve up to about 5 kilometers of draw distances. Internally, forests are divided into blocks. Each block is 1 kilometer. And there are about 16,000 trees per block. So in effect, we have a jittered grid where each tree is about 8 meters apart from one another. So let's take a look under the hood. We have two main phases of rendering forest imposters. The first phase is to update a so-called forest map. So as I said, we have 128 trees per dimension in the block, and that means our forest map has to have the same dimensions, or it has 128 texels per dimension. And each texel stores information for each individual tree. For example, what type of a tree it is, if any, because sometimes the tree may not spawn, it may be destroyed, etc. And other things like randomized offset, rotation, hue, and things like that. So that's phase one. Phase two is interesting because that's where we actually render the geometry itself. So the way this works is that we have a pre-made vertex buffer that stores these standalone quads, one for each tree, and they're positioned in a uniform grid. So the vertex shader can then read the position of a vertex and use that to fetch information from the forest map. For example, the type of the tree. And then it uses this information to sample another set of buffers, which was created during baking, which is an offline process. And this tells the shader the correct offset of each vertex, its UV coordinates. And together with all this combined, the vertex shader can then reshape the geometry, place it into the right position with the correct aspect ratio and with the correct UV coordinates. So that's about it for the vertex shader, and the pixel shader is also interesting. So early on we faced a decision. Should we use 8 directional cross geometry, so basically 8 quads in the same position, just rotated, or should we use a single quad, which is facing the viewer? So obviously cross geometry would be slower because there's more of it. But using a single quad would lack any kind of parallax effect. So again, our approach was to combine the best of both worlds. So we do render a single quad, but during our baking process, we take snapshots of an actual 3D model from 8 different directions by rotating the view around it. And this allows us to do a trick in our pixel shader where we cast a ray against these virtual crossed polygons. And this not only allows us to determine the correct slice of a texture to sample, but also to take account of perspective correction. Now, this is also not a new technique. It was mentioned in the Gama Sutra article called interior mapping. But we do another thing here is that we actually cast 2 rays. 2 rays which are nearest to the position of the viewer. And then we just blend the results. So the end result is something like if you try to read a printed 3D comic book with those funny glasses, and then you would see a 3D image. And then if you look a bit to the left or a bit to the right, you would see how the image changes, and it looks like a hologram. So this is basically the same thing. And one of these images is the 3D model, and the other is an imposter. And honestly, I don't know which one is which anymore. I mean, they're actually quite good. So as I mentioned, we take snapshots of our models. We have several types of textures that we take. That's albedo texture, subsurface, normal map, ambient occlusion, and also depth. So why do we have these many types of textures? Because we evaluate the exact same lighting model for our imposters as we do for the actual 3D models. And it's basically a version of Disney's PBR lighting model. But on top of that, the depth map proved to be very important because you can see here, this image on the left it looks kind of flat because it lacks correct self-shadowing. But if we are able to reconstruct actual depth and use it to calculate correct self-shadowing, you have this nice feeling of a volume on the imposters.
A final thing to mention about trees and imposters. So yeah, our imposters are fast, but our terrains are too big to always render imposters. So after a certain distance, even the imposters become too expensive. So we have a small trick to use here. After a certain distance, we don't render any imposters. We instead bake a special material into the ground that pretends there are forests in the distance, when instead we only have a different material on the ground. And there's another feature, because our subsystems of the terrain are pretty intertwined most of the time. We have a special set of materials related to forests. So whenever a forest spawns, we use the same parameters to set this type of material under the forest. So we can have different, like, muddy terrains, special grassy terrains under the forest to give it the forest feel. So moving on, we'll see some footage here. This is a comparison of imposters and real tree models. And as Robert said earlier, we can't tell the difference, actually. Moving on, we have the plant system. It's basically the same as the tree system. It uses some parameters and combines it with noise to spawn plants in certain areas, certain vegetation densities, or certain elevations. So this allows us to spawn small plants on meadows, small plants on forest entrances, inside the forest themselves, crops on patches. We'll see patches later. The main thing that allows us to do most of this without wasting many man-hours, so this is a huge workflow accelerator in itself, is the editing we mentioned earlier, multi-resolution editing of vegetation density. So an artist comes, uses a brush, and just paints different vegetation levels on the terrain, and this auto-generates plants, trees, grass, different materials. So we get these huge patches of plants with just one brush stroke. So it's pretty effective.
Okay, so we also mentioned that we have a system for rendering grass. The cool thing about this is that it's actually real, true geometry. So each individual blade of grass is a mesh. The way this works internally is actually fairly similar to how forest imposters work, so I'm not going to go into too much detail. I'll just cover a few high-level concepts that are kind of cool. So for example, we have access to our material maps and textures from the shader that renders the grass. And this allows us to determine the type of grass that a material should spawn. So we can have different types of grass or no grass at all if it's a kind of a dry material. So this gives us two things. For example, you will never have grass growing from out of a rock. And second, we are actually able to follow the exact contour of a border between any two materials, which gives a very natural and convincing result. So another thing is that we are also able to sample the color of the material itself, which again has a twofold benefit. First, we have variation. So each individual blade of grass has its own unique color, and so that way you don't have that uniform look of grass. The second cool thing is that this allows us to seamlessly transition from having grass to not having grass, because obviously we can't render grass to an indefinite distance because we're limited by geometry. So at a certain point, we just basically melt the grass and it fades completely seamlessly into the color of terrain itself. So you have no visible threshold of where the grass stops. And yeah, we have this other cool thing where we basically fake per blade ambient shadow on the floor, which is a big deal because it really connects the grass to the floor or to the ground, and without it, it would look unrealistic.
So, moving on, a short overview of one or other.
Sorry, I skipped a slide. No, we actually have something fairly related which renders flowers. It's basically the same code path. So, but the thing here is that it's actually alpha tested geometry because it would not make sense to model each individual petal. But you know that's about it. The only other thing that I could mention is that it's not used only for flowers because you can also define a dry material that says, okay, but I want to spawn little pieces of rock or chips of wood and things like that, and we can model all of that stuff with this basic same system.
So the next subsystem we'll give a short overview of. Roads or paths or similar structures. So we wanted our artists to be able to incorporate these into the terrain so they interact with the terrain. So we added it to the terrain engine. They define splines on the terrain and set some parameters, and we create a road. The road can modify the elevation around it, as you can see on this image. It can modify the materials. It can carry its own materials if you want an asphalt road or something. And it can dry out the vegetation around it, so less plants grow if it's a highway or something similar. It can also carry decals, and we have a whole bunch of other features. For example, we can define lamp posts, bollards, fences, etc. And a related subsystem, as I mentioned earlier, we have patches that are used to define fields and similar structures. The artists just have to place a polygon on the terrain and set the materials it defines and set the other parameters, and we get these nice fields that can also carry crops and other plants.
Okay, so before the end, one last thing. We would like to show you a clip, which is a short preview of all of this technology and more used in our latest and greatest game, Serious Sam 4. Planet Badass. Okay, so thank you for your attention, and I believe we still have time for some questions. I'm sorry?
How many types of GPUs do you use?
How many types of what?
We have only one mic for them, so we'll bring it back to them. But
How many Titan X GPUs in SLI did you use?
No, we actually didn't use any. So we still have many optimizations to make, but the game runs fairly fast as it is now, even though it's still early in development.
We have a question over there.
The game looks fantastic from my point of view, but because I played all other Series Sam games and they also contain other biomes, have you thought about ideas of how to basically preset all these different systems that you have to be able to show other biomes beside, which looks like medieval European grass landscapes?
Yes, of course. This is just one of our levels in the newest game. So some levels may contain some snow biomes. I'm not sure. And yeah, the procedural, the parameters itself for the materials, etc., are all very flexible. We can define any type of biome we want. So expect some of those.
Or if I read that question correctly, you're asking where are the sands that Series Sam is known for? We want Egypt.
So you mentioned multiple times that this is pretty much all done on the GPU side, so the procedural generation and the material transitions. So I assume there is a way for all of this to be accessible on the CPU as well, for collision detection as well. And perhaps related, but more importantly, since you use the procedural transitions for the slopes and the materials, how do you define which footstep sounds are heard when you walk across a different side? That has to be CPU accessible, right?
Yeah, great question. We generate everything on the GPU, and whenever something is needed on the CPU, like for example for collision, for detecting different sounds of footsteps, etc., we generate just the materials around the area we need the footsteps in. Or if we need to place some decals on the ground, let's say bullet holes in dirt or on grass or whatever else, we just sample where the bullet hit, generate the materials around that area so we know where to place it or how to place it. Yes, so the algorithm is the same, we just don't generate everything on the CPU unless it's really needed because it's way more expensive, of course. But yeah, everything matches. The same idea applies to trees and tree billboards because you can't have a different algorithm for generating tree models and tree billboards because as you move closer to the billboards or the imposters, they have to match, they have to fade, they have to crossfade. So we have the same algorithm on the CPU and GPU.
Yeah, I'll just add that we had this approach from day one, practically, because without it, you wouldn't even be able to do simple tasks like raycasting to know if you hit something or not. So it was designed that way from the start.
Thanks for the talk, really great. Two questions I would like to add. The first one is more technical. You mentioned that you would sort, let's say, the 8 or 16 or however, which amounts of materials could turn up at a certain pixel or whatever spot. Do you do the splat maps at once and kind of like select per pixel which color or which material would turn out in the end, render this out and use this in a later step to blend the 16 materials, or do you do the complete sorting stuff in the pixel shader in one go?
Okay, so I think I understood you, so I'll answer, and if it's not what you want, just ask differently. So it's actually a fairly complicated question. I mean, I think we could do a talk just about how we actually upsample the materials from the material map, and I'll try to keep it short. So The way it works is that we store all the data, as I said, in quadtrees, and we start with the basic material map size of 33 pixels. And the actual resolution that we want to upsample it to is 512 pixels, because that's the resolution used for the tile which is actually rendered. So we upsample it on the GPU, and in each step of the way, we apply noise. So again, it's a type of fractal noise because we keep adding iteration and iteration. So this material map is just a mask that says, okay, there's going to be a material here, material there. And this works for the hand-painted materials. So once we upsample it to the target resolution of 512 pixels, we then look at it in another pass, which says, okay, but if there was nothing painted, we have to actually generate something. And in this final pass, we generate using a fairly complex set of rules, like what's the vegetation density, what's the elevation, what's the convexity, you know, all that sort of stuff. We evaluate all that, and we say, okay, well, let's just put some kind of material there. And I think that about covers it. Yeah. So is that what you wanted to hear, or? Okay.
You said it.
Oh, second question, okay.
So thanks. And the second question is, did you, before you decided to use noise for, let's say, mountaintops and everything, did you consider like simulating erosion on the GPU and rendering stuff out or anything like that?
No, we started with noise from day one. We use fractal noise for most of our features on the terrain because we can make it look fairly natural. We may use erosion sometimes in the future. We have different parameters like slope and whatnot, so we just may use erosion. We don't know.
Yeah, just remember, key thing here is speed. So this whole thing needs to run in real time. So
maybe we were considering using erosion for the base data, so to get the base rough elevation, the 32 per kilometer, 32 meters per sample. So we may use erosion to generate that in the future. We'll see.
One more question.
How do you handle LOD changes between the tree billboards and the tree models and stuff like that, so it looks smooth and not choppy without any artifacts?
Yeah, so I should answer that because I've been working mostly on that. And again, it's probably a wide enough topic to do a whole talk about all that. It's complicated. I've been at it for 4 or 5 months. It's still not perfect. But basically, it boils down to using screen space diffusion, where we use a specific noise texture to dissolve the image of an imposter, and the inverse of that image to fade in the image of the actual 3D model. And it's tricky because, well, we use something called temporal-based crossfading between LODs. Which looks more natural than just using distance-based, because, and there's also hysteresis involved. So what this means is that if you move a bit closer, and now it should switch to the actual 3D LOD, it doesn't happen immediately. It just happens over a set amount of like 2 seconds or 1 second. And then if you move back, it'll stay that way. You have to move back even further away, and then you'll have to wait those 2 seconds again so that it transitions. And it's a complicated thing where you have to make it work the same way on the CPU, on the GPU. It has to be synchronized and exact and so on. There's a lot of details here. So the core idea is simple, but the implementation can be tricky.
So, sorry, this raised another question. So, did you use diffusion patterns also on fading out the grass as well? So you mentioned that you would turn the color to the terrain color or to match it in the distance so that there's a fade out less noticeable and anything like that. Did you also use pixel patterns like diffusion patterns for this grass fade out?
I mean, it's fairly simple for the grass. We just sample the material around it so it knows which texture, which base color to use. So that's just it. The color of the grass is mostly the color of the ground around it, so it just blends nicely into the ground. Nothing more to it.
Yeah, but we also shrink it.
Yeah, of course.
So simple shrink, no special. Okay, so is that it?
Hi. Since your tree imposters look so good even up close, why use the actual tree geometry at all?
They're good, but they're not that good. You could see the difference up close, but after, let's say, 15 meters, it gets really hard to see the difference.
What he said. Okay, so thank you.
For any further questions, feel free to email us. We just wanted to give a quick overview. There's so much features we didn't have time to talk about. So thanks for coming.
Thank you.